You want your kid to learn programming, but you're not about to hand them a screen for hours every day. That's the bind so many parents are in right now. Here's what most people don't realize. Starting with wooden blocks and cardboard tiles instead of keyboards and code editors isn't a compromise. It's actually one of the smartest moves you can make. My name is Dr. Priya Mehta, and I've spent years watching how children learn computational thinking, and what I've seen might change how you think about preparing kids for Python, JavaScript, and everything that comes after. You're listening to the STEM Lab podcast. Quick note before we get started, everything you're about to hear is researched and written by real people, verified by real experts. But the voice you're hearing right now is AI generated. Just wanted to be upfront about that. If you've been listening to this show for a while, thanks for being here. Honestly, it's what keeps this thing going. And if you're brand new, welcome. We talk about how kids actually learn STEM concepts, what tools work and why, and how to build real skills without the guesswork. New episodes come out every Monday, Wednesday, and Friday. This one's about something parents ask me all the time. How do you teach coding without just parking your kid in front of a screen? Turns out there's a whole science-backed path for that. Let's jump in. When children learn programming concepts through physical objects first, moving blocks, arranging command cards, pressing buttons on a robot, they're building cognitive foundations that make the jump to text-based languages shockingly smooth. I've watched this happen over and over. A 5-year-old arranges wooden tiles to program a path. 2 years later, that same child picks up loops and conditionals in Scratch like they've always known them. The physical memory guides the abstract understanding. So what exactly is screen-free coding? It's learning the core concepts of programming: sequencing, algorithms, loops, conditionals, debugging, functions, without ever touching a digital device. Instead, kids manipulate physical objects: wooden tiles, cardboard command cards, robots that respond to button presses, board games built around computational logic. These aren't watered-down versions of real coding. They're concentrated doses of the exact logical structures that underpin every programming language out there. When your child arranges command cards to make a robot move forward, move forward again, turn again, they're writing an algorithm. When they realize the sequence didn't work and they swap out the third card, they're debugging. Take something like the Cubeto playset. Check the link below to see the current price. It's a wooden robot that children program using colored blocks placed on a control board. No screens, no syntax, just pure computational thinking made tactile. What makes this approach so powerful is that it isolates the thinking from the typing. Kids don't get tangled up in semicolons or syntax errors while they're still trying to grasp what a loop actually does. They build mental models through their hands. This matters especially for children under 8, whose abstract reasoning is still developing, but whose spatial and motor skills are flourishing. Now let's talk about how this actually works. The journey from physical coding to text-based programming relies on something called embodied cognition, the idea that physical experience shapes abstract thought. When children physically manipulate objects to create sequences, they're encoding those patterns in motor memory, not just visual memory. Here's what happens in a child's brain during screen-free coding. First, concrete manipulation. Your child holds a forward card and places it in sequence. This is a motor action with immediate spatial feedback. Then, pattern recognition. After several rounds, your child notices that 3 forward commands in a row create predictable movement. They're abstracting the concept of repetition. Next comes mental simulation. Eventually, they start planning sequences before placing cards, running the program in their mind. This is executive function development, the ability to hold and manipulate information mentally. Finally, generalization. When they encounter a repeat block later in a tool like Scratch, they recognize it instantly. The physical memory of doing something 3 times maps directly onto the digital loop structure. This progression mirrors how children learn language. They don't start with grammar rules. They start with sounds, words, gestures. Syntax comes later, after the brain has internalized patterns through repeated physical and social experience. Screen-free coding tools deliberately use universal programming concepts. Sequencing, placing cards or tiles in order, translates directly to writing lines of code in sequence. Loops, repeat tiles, or go back to start commands become for loops and while loops in Python. Conditionals, if blocked then turn right cards, map onto if-else statements. Functions, reusable subroutines on separate cards, translate to function definitions in text-based languages. Something like the Code and Go robot mouse activity set uses these exact structures. Check the link below for pricing. Children build mazes and program the mouse with directional cards. Sequence, trial, error, refinement. When they later see move_forward with parentheses in Python, it's not alien, it's just the card they used to hold, now written as text. One of the most underrated benefits of physical coding is how it normalizes debugging. When a robot doesn't follow the intended path, children can see exactly where the sequence broke down. They pick up the incorrect card, replace it, and try again. No error messages, no frustration from typos, just direct visual feedback. This builds what I call debugging confidence. By the time they encounter syntax errors in Arduino or Python, they've already internalized the problem-solving loop. Test, observe, identify the error, fix, retest. The medium has changed, but the thinking hasn't. Moving on to why screen-free coding actually matters for text-based programming. You might wonder, if the goal is Python or JavaScript, why not start there? Why take the detour through wooden blocks and cardboard cards? The answer is cognitive load. Text-based programming demands simultaneous mastery of multiple skills: typing, syntax, abstract logic, and often math or coordinate systems. For a 7-year-old, that's overwhelming. Screen-free coding unbundles these demands. When a child learns programming concepts through tactile tools first, they're only managing the logic. They're not also managing typing speed and accuracy, syntax rules like where the parentheses go, debugging cryptic error messages, or navigating an IDE interface. Once the logical structures are internalized, once loops and conditionals feel intuitive, adding syntax becomes a translation task, not a conceptual leap. I've seen 8-year-olds transition from the Osmo coding starter kit to Scratch to Python in less than a year, precisely because they weren't learning logic and syntax at the same time. Check the link below for current pricing on that kit. Screen-based coding for beginners often involves a lot of failure. Missing a single character breaks the entire program. For children with developing executive function, this can be demoralizing. Screen-free tools, by contrast, offer gentler failure. The robot goes the wrong way, but it still moves. Your child can see what happened and adjust. This builds resilience and iterative thinking, the habits that separate persistent programmers from those who quit after their first error message. Here's the part that matters long-term. The progression from physical coding to text-based programming mirrors how professional developers actually work. They don't start by writing code. They sketch algorithms, draw flowcharts, pseudocode on whiteboards. They think through the logic before typing. Children who learn this way are practicing real engineering habits. By the time they reach Arduino or Python scripting for robotics, they're not intimidated by the blank editor. They know the logic already exists in their head. The code is just notation. Now, let's look at different screen-free coding approaches and what they prepare kids for. Not all screen-free tools are created equal. Some emphasize sequencing, others focus on spatial reasoning or logical operators. Choosing the right approach depends on your child's age and where they're headed. Command card systems, tools like Cubeto, Code and Go Robot Mouse, and ThinkFun Codemaster Programming Logic Game use physical cards or tiles that represent commands. Check the links below for pricing. Children arrange these in sequence to solve puzzles or navigate mazes. What they teach: linear sequencing, basic loops, debugging by observation. The text-based equivalent would be Python's procedural scripts, where each line executes in order. The mental model of read top to bottom, execute each command, transfers directly. From a practical standpoint, they run on batteries, typically AA or AAA, no connectivity required, fully offline. Durable for repeated use. Most components are wood or thick cardboard. Board games with algorithmic rules, games like Robot Turtles and Code Monkey Island, require players to plan multi-step sequences and anticipate outcomes before executing moves. What they teach? Planning ahead, conditionals like if this happens, then what, and function-like reusable strategies. The text-based equivalent would be JavaScript conditionals and functions. Players learn to encapsulate repeated actions, essentially creating their own functions before they know the term. No power requirements, no consumables. These are standalone experiences, but excellent for introducing programming concepts socially. Unplugged robotics with button interfaces, robots like Botley or Bbot, respond to sequences of button presses on their bodies. Children program the robot directly, then watch it execute. What they teach? Memory, holding sequences mentally, immediate feedback loops, spatial reasoning. The text-based equivalent would be Arduino sketches, where you define a sequence of motor commands and upload them to hardware. The press buttons then run model mirrors the write code, upload, observe workflow. Rechargeable batteries are preferred for long-term use. No screen dependency, works on any flat surface. Highly durable, designed for repeated use. Logic puzzle books and card games, non-robotic tools like binary bingo or algorithm flowchart puzzles teach computational thinking without any hardware. What they teach? Boolean logic, pattern recognition, decomposition of complex problems into steps. The text-based equivalent would be any language with conditional logic and operators. These tools build the mental habits needed to parse structures like if x is greater than 5 and y is less than 10 in Python or Java. Zero power, zero connectivity, zero consumables. Infinitely reusable if laminated or photocopied. Let's walk through a progressive learning path from tactile commands to text syntax. The transition isn't a leap, it's a bridge built from carefully sequenced skill milestones. Here's what that path typically looks like. Ages 4 to 6, foundational sequencing. The skill outcome is understanding that instructions happen in order and produce predictable results. Tools include Cubeto, Robot Turtles, Bbot. The capability milestone: your child can plan a 5-step sequence mentally before executing it. They understand that changing the order changes the outcome. What's next? This foundation makes Scratch's block stacking interface feel familiar, not foreign. Ages 6 to 8. Loops and conditionals. The skill outcome is recognizing repeated patterns and using if-then logic. Tools include Osmo coding games, Codemaster, screen-free coding challenges with repeat and if-blocked tiles. The capability milestone: your child can solve puzzles requiring nested logic, like repeat 3 times, move forward, if path is clear, then turn right. What's next? Scratch's loop and conditional blocks map directly onto these physical experiences. The syntax is new, but the logic is not. Ages 8 to 10. Functions and variables. The skill outcome is creating reusable subroutines and tracking changing values. Tools include advanced screen-free challenges, hybrid tools like Osmo Coding Duo, or transition tools that introduce variables through physical counters or markers. The capability milestone: your child can design a multi-step solution, test it, identify inefficiencies, and refactor by creating a function, a repeatable sequence they name and reuse. What's next? Text-based languages like Python, or block-to-text tools like Scratch's See Inside Code View. At this stage, typing out def move underscore sequence with parentheses and colon feels like naming a card they used to hold. Ages 10 and up. Full text-based programming. The skill outcome is writing, debugging, and iterating on code in Python, JavaScript, or C++ using Arduino. Tools include Arduino kits, Python-based robotics platforms like those compatible with Raspberry Pi, or software projects in editors like VS Code or Python Idle. At this stage, your child is using the same tools as professional developers: Arduino for embedded systems, Python for data science and AI, and JavaScript for web development. Now, what should you actually look for in screen-free coding tools? As with any STEM investment, durability, expandability, and compatibility matter. Screen-free coding tools should support repeated use, integrate into a broader learning path, and offer clear progression toward text-based platforms. Power and connectivity. Best for long-term use are rechargeable battery systems, USB-C or micro USB. Robots that rely on disposable AA batteries become expensive over time. True screen-free tools are fully offline, no app required, no firmware updates, no subscription. This is ideal for younger learners and for families managing screen time. If the tool eventually connects to a screen-based platform like Osmo games that pair with iPad apps, ensure it supports your devices. iOS versus Android, Windows versus Mac OS, and Chromebook compatibility vary widely.
Durability and reusability. Materials matter. Wooden components like those in Cubeto outlast plastic in repeated use. Thick cardboard like Robot Turtle's tiles lasts years if stored properly, while thin paper wears quickly. Avoid pits that require proprietary cards or tiles you'll need to replace. The best tools are self-contained. Can you add challenge cards, new maps, or integrate the tool with other STEM kits? Some screen-free robots work with Lego-compatible bases, extending their lifespan as your child's skills grow. Age-appropriate skill progression. Don't just look at the age range on the box. Ask, what specific skill does this teach, and where does it lead? A 4-year-old using Cubeto should, within 6 months, be able to plan sequences mentally and debug simple errors. If they can't, the tool isn't challenging enough. An 8-year-old using Codemaster should be ready to transition to Scratch within a year. If they're still solving the same puzzle types after 6 months, they've plateaued. Let's talk about common pitfalls and how to avoid them. Even the best tools can fall flat if they're introduced at the wrong time or without proper progression. Pitfall 1. Skipping the screen-free stage entirely. Parents sometimes assume that starting directly with Scratch or Python will save time. It rarely does. Without foundational logic, children get bogged down in syntax and interface navigation. They learn to copy-paste code without understanding it. Solution: spend 6 to 12 months on tactile coding before introducing any screen-based tools. The investment pays dividends in comprehension and confidence. Pitfall 2. Treating screen-free coding tools as toys rather than skill builders. If a child plays with a coding robot once and then it sits on a shelf, they've learned nothing. Solution: integrate screen-free coding into a weekly routine. Set challenges, track progress, celebrate milestones. Treat it like piano practice, not recreational play. Pitfall 3. Transitioning too early or too late. Moving to text-based languages before a child has internalized loops and conditionals leads to frustration, but waiting too long can bore an advanced learner. Solution: watch for capability milestones, not age. When your child consistently solves 10-step problems, debugs independently, and asks, "How do I make it repeat forever?" that's your signal to introduce Scratch or block-based tools. Pitfall 4. Ignoring subscription and consumable costs. Some hybrid tools, Osmo for example, require ongoing purchases, new game tiles, app subscriptions, device upgrades. Solution: calculate total cost of ownership over 2 to 3 years. One-time purchase kits like Cubeto or Robot Turtles cost more upfront but have 0 recurring fees. Now let's tackle some frequently asked questions. Can screen-free coding really prepare my child for Python or JavaScript?
Yes, absolutely. Screen-free coding teaches the foundational logic structures, sequencing, loops, conditionals, functions that underpin all text-based languages. When your child transitions to Python, they're not learning entirely new concepts. They're learning how to express familiar patterns in text syntax. Studies in developmental psychology show that children who learn programming concepts through physical manipulation first achieve faster comprehension and make fewer conceptual errors when they begin typing code. At what age should my child transition from screen-free coding to text-based programming? Most children are ready to transition between ages 8 and 10, but age is less important than skill milestones. Look for these signs. Your child can mentally plan 10-plus step sequences, debug errors independently, explain why a sequence didn't work, and express interest in creating more complex programs than their physical tools allow. If they're asking, "How do I make it do this?" and the answer requires variables or nested loops, it's time to explore block-based tools like Scratch, which serve as a bridge to text-based languages. Do I need to buy multiple screen-free coding kits, or is one enough? One well-chosen kit can provide 6 to 12 months of learning, but progression typically requires 2 to 3 tools over the early childhood years. Start with a simple sequencing tool for ages 4 to 6, add a kit with loops and conditionals for ages 6 to 8, then introduce function-building challenges for ages 8 to 10. Each kit targets different cognitive milestones and prepares for the next stage of complexity. The investment is modest compared to screen-based subscription platforms, and the tools are reusable across siblings or can be resold. Will my child lose interest in screen-free coding if their friends are using iPads or tablets? Not if you frame it correctly. Position screen-free coding as engineer mode or real programmer thinking, the way professionals plan before they type. Emphasize that they're building skills their friends haven't learned yet. In my practice, children often feel pride in solving physical puzzles their peers can't, especially when they later demonstrate how quickly they pick up Scratch or Python. Also, many children genuinely prefer tactile tools. The immediate, screenless feedback satisfies their need for hands-on exploration. Some screen-free coding tools can integrate with Arduino or Raspberry Pi later. Some can and some can't. Look for tools with expandability features, robots that accept modular attachments, coding challenges compatible with Lego builds, or systems that explicitly market themselves as Arduino-ready or Raspberry Pi compatible. For example, children who master sequencing and functions on screen-free robots often transition seamlessly to programming Arduino-based robots in C++ because the logic is identical, only the interface changes. So here's the thing to remember. The path from physical coding to text-based programming isn't about replacing tactile learning with screens. It's about layering increasing abstraction onto a solid physical foundation. Your child's hands teach their brain what a loop feels like, what a conditional means, what debugging requires. That embodied knowledge doesn't evaporate when they sit down at a keyboard. It guides every keystroke. When you invest in screen-free coding tools, you're not delaying real programming. You're giving your child the gift of deep comprehension, the kind that doesn't crumble when they encounter their first syntax error or logic bug. You're teaching them to think like engineers before asking them to type like programmers. The children I see who thrive in text-based programming aren't necessarily the ones who started coding earliest. They're the ones who built mental models slowly, physically, patiently. They're the ones who spent months moving wooden blocks before they ever wrote print open parentheses, open quote, hello, comma, world, exclamation point, close quote, close parentheses. That's not a detour. That's the foundation. That's it for this episode of the STEM Lab podcast. Thanks for listening. New episodes drop every Monday, Wednesday, and Friday. So if you want to keep up with what actually works in STEM education, hit subscribe or follow so you don't miss the next one. And if this episode helped you out, I'd really appreciate it if you could leave a 5-star rating and a quick review. It's genuinely the main way other parents and educators find the show, and it makes a bigger difference than you'd think. Thanks again, and I'll see you in the next episode.